Okay, here we go again. I'm going to record another voiceover in addition to the second video that I'm asking you all to watch today. This one comes from Krista King, and she's talking about some other trigonometric identities.
Of theta. So by definition, cotangent theta is always equal to cosecant theta divided by secant theta. The next one we want to talk about is Pythagorean identities, and this one also comes directly from our right triangle. The reason we call them Pythagorean identities is because they're based on the Pythagorean theorem, which remember tells us that a squared plus b squared is equal to c squared. Well, in that formula, that Pythagorean formula, a and b are the lengths of the two legs of the triangle, and c is the length of the hypotenuse. So instead of a, b, and c, if we use x, y, and r, respectively, we can say that the Pythagorean theorem for this right triangle in particular is x squared plus y squared is equal to r squared.
And so what I want you to pretend here is that this is a right triangle drawn inside of a circle. Now, if the radius was equal to 1, that circle would be called a unit circle, but she's going through an example here describing this triangle inset in any sized circle, so any size circle R. And as you watch her derive the identity, now again, we're talking about deriving identities here. This is a geometric description of some behavior of side lengths, and we're going to use this geometric description to establish our trigonometric identity. And this process is something that we're going to see on Thursday of this week, establishing another set of trig identities. So on Thursday, I'm going to walk through an example in which we identify what we call even and odd identities using a circle as well. And a lot of times they start off by being geometry problems, and we investigate from there.
Remember though, before when we were looking at our 6 trig functions, we said that sine of theta was equal to opposite over hypotenuse y over r. Well, if we multiply both sides by r, we get r sine theta is equal to y. And that's important because here we have our Pythagorean theorem and we have a value for y. We're going to end up substituting this into y. So we have that value. Remember, we said also that cosine of theta, cosine was adjacent over hypotenuse, so that was x over r. And if we multiply both sides by r there, we get r cosine theta is equal to x. Now, if we substitute both of these values into our Pythagorean theorem, we know x is r cosine theta, so we get r cosine theta quantity squared. We know y is r sine theta, so we get r sine theta quantity squared. And then we have r squared on the right. When we square both,
So now you can see the transitions. She's changing from the geometric description to the trigonometric description. So instead of x's and y's, we're now using cosine of an angle and sine of an angle. And she's just going to continue to simplify from here.
both of these, we get r squared cosine squared theta plus r squared sine squared theta equals r squared. And then when we divide through each term by r squared, we get these three r squared terms to cancel, leaving us with just 1 over here on the right-hand side because r squared divided by r squared is 1. It's not 0. So then we get cosine squared theta plus sine squared theta is equal to 1. And this is the first of 3 Pythagorean identities, but realize that this just came directly from our right triangle. So if we can remember SOHCAHTOA, we can get to sine theta is y over r and cosine theta is x over r. We can solve those for y and x respectively, and then we can plug those into the Pythagorean theorem, x squared plus y squared equals r squared, to get to this Pythagorean identity. So we can either memorize this or we can just derive it directly from the right triangle. Now there's
And I really like what she said at the end there. You can either memorize these Pythagorean identities, and this is just one of the three. You can memorize them, or you can derive them yourself as you need them. Now, as it turns out, this is the by far the most popular Pythagorean identity. You'll have this memorized if even if you don't have it memorized already. So that'll be memorized very very soon. The other two identities are some that you may have memorized or you may end up deriving each time that you need them. Now, she's going to walk through the derivation of one of the trig identities, and then I'm going to ask you to do the last trig identity on the worksheet itself. So let's take a look.
two more Pythagorean identities that are similar to this first one. You could memorize those as well, but here's a really easy way to remember them or come up with them if you can't memorize them. So what you want to do is you want to divide through this equation by cosine squared. Then we're going to get the other identity by dividing through by sine squared. So let's see what happens if we divide this whole thing through by cosine squared. Well, we would get cosine squared theta over cosine squared theta plus sine squared over cosine squared is equal to 1 over cosine squared theta. Well, cosine squared over cosine squared is 1. Remember that sine divided by cosine is the same as tangent. So sine squared divided by cosine squared is going to be tangent squared. So I'll get tangent squared theta. And then 1 divided by cosine, remember from our reciprocal identity, 1 divided by cosine is the same as secant. So 1 divided by cosine squared will be secant squared. So by dividing the first Pythagorean identity through by cosine squared, we were able to come up with the second Pythagorean identity. To get the third one, we're just going to
So let's see if we can come up with a third one on our own, and then we'll resume her video to see if our ideas agree with one another. So if we start with the original trig identity, sine squared theta plus cosine squared theta equals 1. And you could reverse these two depending on your preferences. I almost always write sine squared plus cosine squared, although we might see it written differently. But if we start with that original Pythagorean identity, the hint was to divide this time by sine squared instead of dividing by cosine squared like we saw in the video the first time. So if we divide both sides of the equation, or all terms, by sine squared of theta, clearly this fraction on the left has the same numerator as denominator, so when those two divide, they simplify to equal the number 1. And if it wasn't real clear why this is going to turn into cotangent in this case, let me just remind you, cosine squared and sine squared are really just cosine of theta times cosine theta, and sine theta times sine theta. And in a sense, we've got of the same two of the same fractions that are multiplying here. And cosine theta over sine theta, if we reference back to our list of identities, this is why I like having them written down so that we can reference them at another time. Well, here's where we see cosine theta and sine theta, cosine over sine. And if I see cosine over sine, then I can simply rewrite that as cotangent. And so that's what she was describing in the last example of the video. So these two both create tangent. So I'm going to kind of get ahead of myself here and write this cotangent twice. So this is cotangent theta times another cotangent theta. And now I'm going to try to catch up on the right-hand side. Similarly, we've got 1 over sine theta times another 1 over sine theta. And again, by definition, or by looking at our prior trig identities, here's 1 over sine theta. 1 over sine theta is indeed equal to cosecant theta. So we can write this as cosecant theta times cosecant theta. And rather than listing these separately, running out of room here, so I'll slide this over to this side. We'll write this as 1 plus cotangent squared of theta equals cosecant squared of theta. And that should be the third trigonometric identity, although our orders slightly differ from one video to the last. And certainly we do have 1 plus cotangent squared equals cosecant squared. So we've just now established this third identity. It is worth noting, excuse me, it's worth noting again, I've mentioned this in the past, but in case you forgot or if you didn't pick up on it the first time, when we write a trig function, let's say sine function, if that function itself needs to be multiplied by itself, if we're squaring that function, the accepted notation is to write this without parentheses and instead include the squared symbol in between the trig function and the variable. So this is just a little side note here. When you see or when you have a function that's being squared, on paper we tend to write it as sine squared theta instead of sine of theta squared, or if this was cosine or any of the other trig functions, that would be the same as well. So on paper we tend to write it this way. However, in most calculators, and this is kind of the frustrating part, in most calculators, we have to type in our expression this way. Most calculators don't understand this intermittent or in-between square. They prefer to have the parentheses around the function and squares on the outside. So just be aware of that. If you're using a calculator like a TI-84 or something like that, you will have to write it on the left-hand side.
Divide through this first equation by the other trig function, sine squared. So if we divide this through by sine squared, we'll get cosine squared over sine squared. Well, cosine over sine, remember from the quotient identity, cosine over sine is cotangent. So we'll get cotangent squared theta. Sine squared divided by sine squared is 1. And then 1 divided by sine squared, remember from the reciprocal identity, is cosecant squared. So cosecant squared of theta. And these are all three Pythagorean identities. Now, these are common enough that you may want to memorize these, especially this first one. This one comes up so often that it's really important to have it memorized. These other two, a little bit less so, but they come up often enough that it would be helpful to have all of these available for memory. But if for some reason you forget the second two, you can just use the first one to build them out really quickly, like we just did. The next one I want to talk about is even odd identities, and I don't want to.
Okay, so this this section of her video is talking about even and odd identities, and the even and odd identities directly correlate to this notion of even and odd functions. So if you recall, an even function by definition is one in that if we substitute a negative x value into the function, then what we're going to get back is the original function itself. Whereas an odd function, if we were to substitute in a negative x value, then we would obtain the opposite of the original function. A function is neither even nor odd if neither of these descriptions are met. Now, when we're talking about the graphs of these functions, remember that even functions are those functions that, as they appear on the right side of our x-axis, right, all of our positive x values, they would be exactly identical on the left side of the graph, so that when we start substituting in negative x values, we end up getting the same y results on both the left and the right side of the graph. When it comes to the graphs of an odd function, you should recall that what happens on the right side or the positive x section of the graph ends up being completely opposite or perfectly opposite on the left. And there's a rotational symmetry in this case. Let me see if I can do that here. There we go. That's pretty close. So as we input an x value on the right-hand side, let's say we plug in this x value and we would get this y value as a result. If I plug in the same x value on the left-hand side, we'd get the opposite result. With that even function, if I plugged in this x value, here's the y value we obtain, and if I plug that into the left-hand side, I get the same y result. Those two are at the same level. So when it comes to our trig functions, they look something like this. And here they are reported on our worksheet. Now, just like we had identities listed at the top, and you may want to consider memorizing those, here's another group of identities that you may want to consider memorizing. These are what we call the even odd identities. And once again, the notion here is that when we see something, say, on the left-hand side of the equation, if that was in a larger problem, it might be beneficial for us to rewrite it in this form on the right-hand side. So I'm going to go back to the video now, and we'll finish listening to her perspective on this set of identities.
The pretty easy way to remember these identities, so I would recommend memorizing these ones. But this whole even-odd identity concept comes from the concept of even functions and odd functions. So remember that even functions are symmetrical about the y-axis. In other words, if the y-axis is a mirror, the function is perfectly reflected across the y-axis. It has a mirror image of itself flipped across the y-axis, whereas odd functions are symmetrical about the origin. So this whole even-odd identity concept is basically saying which trig functions are even and which trig functions are odd. And the trick I use for remembering this is I just think about this chart in my head. We always arrange the chart of the 6 trig functions in the same way. You always have sine, cosine, theta down the left, cosecant, secant, cotangent down the right. So in that order, I'm going to put negative signs in the 4 corners, or here, 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 and here, because
So if you had just copied this chart from her video and then moved on without watching or listening, you may have missed these negative signs. Now, I went ahead and included them immediately when I wrote mine, but if you were just watching her video on your own, you may have missed that.
what this is saying is that instead of sine theta, if I have a function sine of theta, and I substitute negative theta in for that theta, if I plug in negative theta instead, what do I get back? Well, the result would actually just be negative sine theta. And that's an odd function. These 4 functions here are all odd functions. And I just think of the 4 corners as being the odd functions, so my negative signs are going to be here. Whereas the middle row here, my middle functions, are going to be even functions, which means that they have no negative sign. So practically speaking, what that means is that, for example, if I'm simplifying a trigonometric expression and I see cosine of negative theta somewhere in that expression, that's the same thing as cosine of theta. So I can, instead of writing cosine of negative theta, I can replace that value with cosine of theta, or I could replace secant of negative theta with secant of theta. So that'll really help me in simplifying a trig expression that has a negative angle in it like this. And same thing here, if I saw sine of negative theta in one of my expressions that I'm trying to simplify, I could replace that with negative sine of theta. And either way, notice that the angles here always end up positive. I have positive theta, 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 as opposed to negative theta, negative theta, negative theta. So these are really helpful for simplifying, and all you have to remember is which ones are odd, which ones are even, and I just remember that my 4 corners are the ones that have the negative sign. So I just put those negative signs out there, and that helps me remember the even odd identities.
Okay, so on our chart over here, oops, I should have labeled this more clearly. These are even odd identities, and this guy was odd, odd. All at the corners, we were labeling these as odd functions, and on the inner two, we're labeling as even functions. Now, where that might become practical, let's see this. Now, you all should recognize that sine of the angle measure pi over 3, well, that's equal to um, well, the y value at pi over 3. Remember, pi over 3 is this position here, the last one before vertical. So the y value there is square root 3 over 2. If you didn't memorize the entire unit circle, but had to then evaluate sine at negative pi over 3, this is what we're talking about by using a negative angle measure, a negative theta value. By using our even odd identities, since sine is an odd function, we would know that sine at negative pi over 3, sine at a negative angle measure is exactly the same as sine at the regular angle measure, just with a negative sign up front, negative symbol up front. So sine of negative pi over 3 is the same as negative sine of pi over 3. And since we just established that sine of pi over 3 is equal to radical 3 over 2, then sine of negative pi over 3 is equal to negative radical 3 over 2. Now, in our class, we went ahead and memorized the entire unit circle, so when we recognize that this angle measure is negative pi over 3, then of course it becomes obvious that our y result is negative square root 3 over 2. But not all students memorize the entire unit circle. There are some classes that only have you memorize the first quadrant, and then you have to use identities to derive the rest. And we won't be seeing too many of these specific examples in our work. Instead, we're going to be utilizing unknown angle measures and solving for unknown angle measures moving forward. But I thought I'd share that with you just so that you can see the application of this identity in terms of what we've seen most recently. Hopefully you found these two videos helpful to provide a little bit more clarity and instruction on what we're getting into now. The test number 4 and 5 in the past has been combined together, worth a large portion of your overall grade. And with us working from home, this is going to prove to be a bit of a challenge. But as long as you're putting the time in and spending some time practicing on your own and making sure that you ask questions as you come up with them, I'm certain that you'll be able to make your way through this. So good luck to you the rest of the week, and I'll probably put together a couple more of these videos so that you can reference them later. See you later.